Okay, welcome to part 3 of this class. So we have covered the invariant points, the eutectic microstructure. We talked about the iron-carbon phase diagram, and we made an example with an hypereutectoid steel, and we work out about the primary phase and the microstructure that was developed for this steel. So now we'll talk about the TTT diagrams, or time temperature transformation diagrams. When a material transforms from one phase to another, transformation is not instantaneous. A certain time has to pass for transformation to take place. Have you ever freeze something in your fridge or your freezer? So you know that if you have a Coca-Cola can with a liquid and you put that Coca-Cola can in the freezer, it will take some time before it becomes solid. So transformation is not instantaneous. It requires a certain amount of time for it to happen. So that's also true for any transformation, regardless of the materials. So we can plot how long it takes for a transformation to happen. And that graph looks like this. This is a typical transformation graph. We can see that the starting of transformation will take some time. So this is like the starting of the transformation, and it will start to develop slow pace at first. Then it will reach a certain speed, steady speed. But as you approach the final part of the transformation, the speed will start to be slower. So the final part will take longer to happen. So from the experimental point of view, sometimes you have to stop the experiment when you reach 99 or 98 or 99.9 rather than waiting for the 100% transformation. So by plotting these transformation curves for different quenching temperatures, we can construct a graph known as the temperature time transformation diagram, or TTT diagram for the short. Quenching means a sudden drop in temperature from a higher value to a lower one. So for construction of TTT diagrams, transformation curves are constructed with quenching always starting at the same highest temperature. So we wait at that high temperature until an equilibrium is reached, and then from that temperature we make the quenching, and we maintain the quenching temperature, and then we analyze how the phase is being transformed. How do we know that a transformation is taking place and how much has advanced? In order to do that, we have to employ additional techniques. So it's not just like using a microscope of hot platina, that's the name for the microscope. So with that microscope, we can actually see what is happening. So we can make a photograph or a micrograph from the situation at different times. And for each time, we then calculate the fraction for the phase transforming. So we can translate for every picture that we are taking. So for that time, how much of the transformation has taken place. That's one way of doing it. Another way of doing it is by using X-ray diffraction. So we apply X-rays to the sample and check how much of that has been transformed. Or we can use, as we saw last week, differential scanning calorimetry equipment, so we can find out how much energy has been absorbed, and by looking into the energy usage and the time, we can translate that information into how much of the transformation has taken place. So there are different ways from the experimental point of view to know how much of the transformation has taken place. So let's try to construct a temperature time transformation diagram for the eutectoid steel. So we know that eutectoid steels have the eutectoid composition that happens at 0.77 weight% carbon. So where do we start to make this TTT diagram? So first of all, we have to start with a material that has one phase, in this case austenite. So we need to create 100% austenite. So we know that we have this steel with 0.77 weight% carbon. So we have to select a temperature in this region. So any temperature in this region will create a material with 100% austenite. So we can use anything above 727. Now it is a common practice to use at least 50 Celsius above the transformation temperature. You can then select, I don't know, 777, 780. So you can see in many books that some TTT diagrams are constructed using 800 Celsius. So the selection will vary. But anyway, the idea is for you to start with 100% austenite. So we'll select 800 Celsius as the austenizing temperature. And we have to wait there for a certain time. As a rule of thumb, we have to wait at least 15 minutes per quarter of an inch in thickness for a material. With all this in mind, so we are now ready to start with our experiments, okay? So for constructing this temperature time transformation diagram for the eutectoid steel, let's start by quenching this material to, let's say, 675 Celsius. So that means that we have our material starting at this temperature, and we'll quench the material to 775, about this. So we start here at about 800 Celsius. So we quench up to here, which is about 675 Celsius. So we do this in a very, very fast way. How we do that in practice? Normally we have a media, a liquid media at this temperature. Could be a molten salt, like molten sodium chloride, or it can also be a molten metal, like lead, zinc, or some other metals that are liquid at the temperature of interest. You can also use oil, because oil can be heated to higher temperatures than 100 Celsius. So there are different ways of doing this. But the idea is that you have to find a media, liquid normally, and for that media, it has to be at the right temperature. You have to be able to control the liquid to remain at that temperature every time, and for as long as you are doing the experiment. And you just drop your material from the high temperature to this low temperature. So it's quite interesting, the experimental arrangement for doing this, or the industrial way of doing it. You can do this also in an industry. So we quench the steel from 800 to 675 Celsius, and then by using the hot platina microscope of the X-ray diffraction or whatever we have at hand, so we start to measure the transformation. So for this example, let's say that we are noticing that when we have 40 seconds for the experiment, then the transformation starts to happen. So 40 seconds, this is 10, 20, 30, so 40 seconds is right there. So we see that there is a change in the microstructure starting at 40 seconds, and then we continue to measure the transformation. So we have different points for this transformation, and then we decide that the end transformation happens or finishes at about 2000 seconds. So this is just an example. You can imagine that in real experiments they are more careful with that. They might say that, then we'll say that the finishes are at 98% transformation, or whatever value they decide this is the finish. So now we have knowledge that when we quench from 800 to 675, transformation starts at 40 seconds and transformation ends at 2000 seconds. Okay? So we repeat the experiment. So we again heat the material, always starting at 800 Celsius, and we quench to different values. Our first experiment was for 675, second experiment 650, the third experiment 540. Why the graph is shifting to the left? So the higher the quench, the higher the nucleation. Why is that? You have to remember that the critical radius is proportional to the undercooling value. So the higher the undercooling value, the lower the critical radius. So it's easier for nucleation to take place. You also notice that in the fourth experiment, you have a shift now to the right, and for the fifth experiment, we have a shift further to the right. Why is that? I will not answer that at the moment. We'll see that a few slides later, but try to think about that and figure out your answers and contrast your answers with what we'll discuss in a moment. So now we have different experiments, and for each experiment we'll have different values for the start and different values for the end. Okay? So let's concentrate on those starting times and ending times for each of the temperatures. So for 675, we've seen that the start it's 40 seconds and the end is at 2000. For 650, the start is about 1, 2, 3, 4, 5, and the end is at 40 seconds, 10, 20, 30, 40. So we continue to do that for each of the graphs. So now that we have the start and end points for each of the temperatures, we can start to construct our temperature time transformation diagram. So 675, so this is about 675. The start is 40 seconds, which is about this value. And the end is here. What happens in the middle? Well, in the middle, you are with a fraction of the transformation. And you can know how much you have of that transformation by watching the transformation curves. So every time that we make an analysis, 650, the start and the end, 540, the start and the end, 425, the start and the end, 350, start and the end. So if we connect all the start lines, so we call this the start of the transformation. Of course, this is the finish line or end of transformation. This is just as a reference. This is the 727 Celsius temperature. So we know that everything above this temperature is austenite. So below that, austenite is being transformed in watts. In this case, we know that below 727 Celsius, austenite is being transformed in pearlite, which is the eutectoid phase. So we know that this is pearlite. Know that pearlite is a mixture of ferrite plus cementite. So in many TTT diagrams, they use this ferrite and cementite, but you have to remember that this is called pearlite, because when you are talking about ferrite and cementite, then you have to remember that you have the possibility for producing primary ferrite or primary cementite. That's not the case for the eutectoid steel, because the eutectoid steel has the eutectoid composition, so there is no possibility for primary phases. So you will reach the invariant point, and from that invariant point you will get directly pearlite. So there is nothing in the middle. But for TTT diagrams, which are for hypoeutectoid steels or hypereutectoid steels, then you will have primary phases. Not the case for this eutectoid steel. So in the middle, you have a mixture of austenite and pearlite. So this is our TTT diagram, and you can construct this for lower temperatures for quenching. So the full diagram is this. This is the actual TTT diagram for the eutectoid steel. So this is an isothermal transformation diagram. You can see that it is very close to the 0.77 weight percent carbon that we need for the eutectoid composition. In this particular case, the austenitizing temperature was 900 Celsius. In our exercise, we were using 800, so they were using 900 Celsius. And they also have a grain size of 6. So we can see that this is the limit between austenite and the pearlite, which in our exercise was 727 Celsius. So when you are quenching, you have to think in a very peculiar way. So quenching is lowering the temperature from high temperature to a certain value, let's say 800 Celsius, and then you have to wait. So in this example, if you quench from the austenizing temperature to 800 Celsius and you wait, in this example, 100 seconds, then you will have full transformation. So the material will be 100% pearlite. You can see that in this diagram, they are talking about ferrite and cementite, which is also known as carbide. So they aren't telling you that this is pearlite. We know it is pearlite, but they just use the traditional way of saying it, ferrite and carbide, but we know it is pearlite. So in using these diagrams, you have to think about quenching, which is a straight vertical line, depending on the temperature that you are quenching. Then you have to wait for transformation to happen. If you wait only this amount of time, then transformation will not start. Transformation needs more time for it to start. Now there are two new lines here. This dashed line that you can see here, and there is a particular reference to this, which is MS. This is reference to Martensite transformation. So MS means that Martensite transformation starts. So if you quench from high temperature to anything below this temperature, you will start to form Martensite. What is Martensite? If you remember from your homework, from the notes, from the readings, you have your gamma iron, which is iron FCC, and when you decrease the temperature below 727, you will have iron BCC or ferrite. So when you are transforming and you give enough time, so you are under equilibrium conditions, so you have very long waiting times. So you have time for the crystal to be transformed from phase center cubic to the body center cubic crystal structure. But when you are quenching, you have very little time. Time is very little. So the crystal will not be able to accommodate the atoms which are at the faces to other places. So these atoms won't have time to travel and to create the body center cubic crystals. So you will have something that it is called Martensite. And remember that Martensite is BCT crystal distorted. So I had a very distorted crystal. So it's a tetragonal cubic body center crystal, but it's really distorted. The carbon atoms normally are somewhere there in the crystal, so the carbons didn't have time to travel to the proper positions, and the irons also didn't have time to travel. So you have a very, very distorted crystal, which is called Martensite, which, by the way, is very, very strong because of the residual stresses acting in the crystal structure, but fragile because lots of residual stresses are there. So it's very strong, but brittle. So this is the actual TTT diagram for the eutectoid steel. And as you can imagine, you can play with this. So you might think about quenching in different steps. So the first step might be quenching for 800 Celsius, wait certain amount of time, and then quench again to a different temperature, wait for a different amount of time, and then quench again to a different temperature, and wait a different amount of time. Now, you have to notice that when I say quenching, I'm always moving in a vertical way. Like time is not passing. That's not completely true. So when you quench, you have to think about the material. So you might say that in reality, the material when you are quenching follows a line like this one. So if your quenching is slow, you might end up with something like this or this. So in that case, the transformation will be very complex because you will be passing for different temperatures. So in using these diagrams, you don't consider that. You are considering that the quenching always follows straight line. So when you have different steps in your quenching, you have to consider every step as a new one, regardless of how long you spent waiting in the previous step. Step 1, step 2, step 3. So regardless of how long you took on each step, you have to consider straight line. There are other graphs to work out when this is not a quenching idea like in these cases, which is a very fast quenching. And those are the TTT diagrams that we'll see later today. So this is the end of part 3, and we'll start in a few minutes with part 4.